even light is subject to that. Basically, that the space itself curving around any object. And there are two kinds of space: the space between objects and the space in objects. And it has to bend with reality too.
Pseudoscience.
Well, we can demonstrate it.
Wait, you could demonstrate? Oh, yeah, that's exactly what we're looking for. Hey, I would love to see a demonstration of
gravitational waves were proven this year.
Bending, warping in space-time.
Yeah, we proved that with gravitational waves that were thoroughly proved this year.
Send me that source. I didn't see anything from this year that was thoroughly proven. I didn't even know science proves things.
Well, it doesn't prove things, but that's a colloquial that we found gravitational waves. And so therefore light must bend to those waves. Right? It'll ride the heel of the wave, just like a surfer riding a wave on an ocean.
You're talking about black hole observations?
Well, you can have a black hole or a neutron star or any kind of superly dense, superly packed density will bend the fabric of space-time.
We're talking about what happened this year that they was able to prove gravitational waves.
Well, I believe they had two. I just said the star. Two of those stars that circled each other, and we saw what's the equaling out of the waves on the laser at the same moment they crossed, which canceled the whole wave out. Which that's what happens when two opposite waves are created and they hit each other. They cancel out, and so we observed that canceling out of the wave, which is not proof that there was a wave. It proves that the wave itself was canceled. And that can only happen by super heavy, massive objects.
Okay, so you're saying that they assume that the black holes and these luminary phenomena are super heavy, and you're observing a distortion in the observation, and you're saying that distortion is due to gravity because we're assuming that these luminaries are super heavy. Is that what I'm again?
Well, you're close. It's that you're in the ballpark. It's that the two supermassive stars are circling each other, and as they're circling, they're having trough waves come out from around them. That's the fabric of reality itself is literally like shaking from the force and the power of them. And when they cross a certain point, which is directly aligned with us, then that wave cancels out, and then it picks back up when they circle. And what that shows us is that there are two of them, and they're massive, and the wave is canceling each other out at the exact moment when they point to us. And that's what we predicted to see if there were gravitational waves around supermassive objects in space. So we had a prediction, and then we found it after like 75 years.
That's what they predicted. Brother? Oh, yeah, go ahead, Adam.
You familiar with a first order measurement versus a second order measurement, thirds, etc.?
Yeah.
Okay, so when you look at what LIGO, quote unquote, say that they measured, right? It's not like we're looking at a fringe pattern or something, right? They've extrapolated noise into a system, and then through various layered computer algorithms and neural networks, right? They run algorithms to extrapolate what they think a gravitational wave might look like. And we'll get to the mathematical derivation of that here in a second. But anyway, what they're doing is they have nothing to compare it to in reality. This is all just an abstraction, and then it's run through multiple neural layer networks where it'll come back and be like, hey, is this do I have enough noise to fit what we're looking at here? And they've done this game so many times with this noise and this data and the data injections that people that work at LIGO don't even believe it when they say that they get a detection, right? Because it's literally just noise. And when you realize the process of it, what they're measuring, it could literally be anything. They're saying they're measuring a ripple in time, 1/1000th the width of a human hair. And then we'll touch on interferometry here in a second, but let's go back to the mathematical derivation of it, right? So Einstein's field equations are nonlinear, right? They diverge to infinity. So to solve them, to get meaningful extractions out of them, you have to rein them in and make general approximations to linearize them to get your predictions for them. So gravitational waves are actually, they get canceled out when you try to use curved space-time with them. So you actually have to use a preferred coordinate system to even get the prediction for them. So that when you make your linearizations, so that you can get how much of the ripple you would get to measure, it doesn't get washed out with all your other approximations during the linearization process. Then on top of that, let's see, noise, right? Okay, yeah. So let's get into an orthogonal interferometer setup, right? Now, these giant LIGO interferometers have a very similar setup, right? You familiar with Michelson-Morley?
Yep.
Okay, so same exact configuration, same thing, right? They say, okay, there's no variance in the speed of light, relativity, can't measure linear motion, blah, blah, blah. Oh, maybe the Earth's falling around a gravitational field, et cetera, right? Are you familiar with that whole jumping off point?
Yeah.
Okay, cool. So they say you can't measure 30 kilometers a second, right? But what you can measure is the mass of two black holes colliding around each other that causes a ripple in space-time that permeates for 11 billion years, and that they're going to measure this with a laser using the same configuration that you can't measure 30 kilometers a second with, but you can measure a ripple in space-time, the fraction, or 1/1000th the width of a human hair. And then and to back it up a little bit off of that, right? I don't know how much further you've looked into interferometry or linear setups, so-called linear setups since then, but are you familiar with the work of Dayton Miller, Hector Minera, Yuri Galev, and I think even Picard did one as well.
I know about Picard, know about Yuri. I don't know the other two names.
Okay, so there was a guy named Dayton Miller who repeated the Michelson-Morley experiments, right? Because what they actually measured in that experiment, if you look at the paper, they measured a velocity of 5 kilometers a second. And obviously the heliocentric prediction requires 30 kilometers. So they were like, well, we could just round it to 0, right? Because it's only just over one fringe. Maybe it's just an error, like who knows, right? Yeah. But they also suggest that, hey, we should take measurements at later times in the year to see, if these minimum maximum dimensions change, because we really don't know what we're measuring, or if there's like a group velocity between XYZ, we don't know. So they ended up not continuing anything, but then they redefined all of physics over that, introduced relativity theory by 1905, right? Yeah. Now there was a guy named Dayton Miller who continued the experiments for over 30 years. So he went from 1905 to 1930. And he continued the experiments and doing different controls, doing different times a year, and actually using different apparatuses, different materials, et cetera, to account for controls to really narrow down what he was measuring. And what he found was that the measurement that they made wasn't an error. It wasn't something that should be disregarded and rounded down to 0. What he was measuring was a daily and annual fluctuation that has a periodicity to it that matches the equinoxes when it reaches the minimum and maximum dimensions. So in other words, the speed of light is changing, daily in accordance with sidereal time, and then also it reaches, goes even faster on the equinoxes and then slower on the other ones, so twice a year. And and the velocity isn't within, heliocentric range, so they ignore it, right? They say, oh, Dayton Miller was a quack, he didn't know about XYZ and stuff like that. But before we move on from Miller, one of the last experiments that he did was to confirm his hypothesis about what he was measuring, in terms of the velocity component. He hypothesized that he would get a faster reading at altitude because you would be closer to the source of the motion, and that's what he found. So instead of getting the 5 to 6 kilometers a second that they were getting around 200 feet above sea level, at 1,800 feet above sea level, he got 8 to 12 kilometers a second. And then that was repeated by, the periodicity rather, not necessarily the altitude, but the periodicity. So those daily and annual fluctuations were repeated by Hector Minera in 2002, I want to say. And then there was a guy named Yuri Gallo who did it with a laser interferometer and also radio wave bands and matched that same periodicity. And then back to Picard real quick. So this was like back in the Miller days too, like right before they were, like still in that time period, like in the early 1920s and stuff. Picard took an interferometer up that was, what was it? Oh, it was not symmetrical to like, the Michelson-Morley configuration. One of the arms was longer, and they got a reading of 27 kilometers a second at 1,800 feet. So they took an air balloon to 1,800 feet. So at the same altitude, Miller was getting 12 kilometers a second. So with a asymmetrical configuration, they got 27 kilometers a second, and they rounded that down to 0 and said, no ether wind to be seen here, boys. And it's like, dude, they were so close to that delicious 30, but that asymmetrical configuration kind of ruins it because it's like the whole way that it works is based off of the symmetry of it. But so, they couldn't reproduce it. But it was funny that they threw that out because it was like they almost had it, but then they were like, nah. So that's kind of the history of linear interferometry. If you have any questions or anything like that, love to answer that before we get into SAGNEC and the generalization of it that shows that we can detect linear motion. And then remind me about midnight, noon, redshift, because I think that's one of my new favorite arguments against general relativity because it's super easy to understand.
Well, I'm not saying general relativity is perfect. Not at all. That's why I said we're looking for a grand unified theory. And I don't think it'll be involved in string theory or anything like that. I think.
Oh yeah, no worries.
This is just more accurate. It's more accurate than Newton's laws.
Well, let's talk about Newton's laws real quick on that, right? So there's a concept in physics called kinematics, and kinematics means measurement and predictions of motion based off of those measurements, right? So if you have a velocity and time, you're just going to predict where an object would be based off of its velocity and time, right? Irrespective of the cause of motion. So it doesn't matter if gravity's okay.
Yeah, cool. Whatever the force is, it's still going to be there.
No, yeah, gotcha. So it's just based off of the measurements, no assumption about causal mechanisms is the important part. So Kepler came along with his equations, his laws, and he was like, hey, basically what we have here is we have a proportional ratio with the periodicity of the event, and that will be proportional to the semi-major axis of the orbital body, of the body in orbit around the sun, right?
Yes.
Or not around the sun, but around whatever, right? It just happens to be
whatever the force is,
Yeah, gotcha. So anyway, it's in relation to the periodicity, and the important part of how they did this conversion was the proportionality constant, right? And that's where you take velocity, you take the velocity of the event, right? Because it's how fast it's moving in the sky based over a time, right? So we got to convert that velocity, and they did that by turning it into pi so they could make an orbital diameter, right? So that's where the proportionality comes from with the periodicity. And then Newton came along and was like, hey, boys, did you know that you can introduce mass in there, and we could work out the same proportionality with
energy,
with Kepler's equations? And everyone was like, oh, bet, no way. So when they started applying the equations, right, because of how algebra works, once you have the periodicity and you have the velocity, you can backwards derive the mass off of that, right? So they started applying, using the constants derived from the Cavendish experiment. They started applying that to the sky, right, as a dynamic explanation, right? So moving on from just kinematics, right, not just applying like measurements and proportionality ratios, right, to say like the dynamic cause of the movement now is actually because the sun weighs this much and the earth weighs this much, and because of that relationship, it takes 365 days to orbit the sun. And also based off of that, we get the distance for the 93 million miles because of the proportionality with the semi-major axis, right? So that's how they derived everything, and they assumed, like, they were like, bet this works really good, right? So that's where Michelson-Morley came in, because if you have if Newtonian dynamics applied to the sky were true, there's going to be a velocity of 30 kilometers a second, right? And if you get into the history of interferometry, you'll find that from the Fazal experiment where he demonstrated Fresnel drag, They knew exactly how to measure the velocity of light and fringe shift patterns and measure linear velocity because they measured the translational speed of running water with an interferometer with a proportional ratio to 44% with the moving water and against, not, or, and that's counting refraction index in there as well, right? So this is an effect that's outside of the confines of refraction or whatever. This is proportional to the velocity. So they knew exactly what they were doing with their prediction. And when you look at the equation from Michelson-Morley, it's actually the same equation that they use for the Sagnac effect to this day in ring laser gyroscopes. So it's that ratio of velocity over c to derive the fringes is it's dead accurate, right? I don't think you would disagree on that.
No, I'm not. So, I wouldn't disagree with that.
Yeah, so they knew exactly what to expect with that. And when they didn't get 30 kilometers a second, I mean, that falsifies Newtonian dynamics applied to the sky because it reveals it to be just an abstraction. And what they'll tell you now, the best argument that I've seen put forward is that in modern textbooks, the mass has to be included. You can't just algebraically cancel it out. You have to reintroduce it. So what they, in the example that they gave, they reintroduced mass for a periodicity of Jupiter's moons, for example. So they reintroduced the mass of Jupiter for it. And what it changes the approximation by 0.0000001% more accurate. Like it's so in other words, there's no difference and it is just canceled out. So it's still just kinematics. It's just disguised as dynamics, and it was experimentally falsified. And then that was reproduced, their experimental measurements were reproduced by other people over the years and even in modern times with modern equipment.
Oh, okay. But wasn't that would work on close bodies of extreme density, but on extremely far bodies, we have to take into account time also, and mass, and direction, and can't remember the other one. But in order to get the spin of any object, we can determine if there's other objects orbiting them. We can detect that. We can detect when, like I said, two of these neutron stars cross paths because they ripple reality. The Jupiter is like 1 billion times smaller than, in density than a neutron star would be. When you get towards those kinds of weights, even Einstein's theories break down into gibberish when you get close to the very curvature of reality bending around those massive objects. I don't know if any other system, including any of Einstein's or anyone else's works, that can determine a future prediction of these objects and the noise of reality bending, other than Einstein's theorems.
Gotcha. Well, I'm glad you brought it back to Einstein there so we could pick up off of that. So as we were learning about the Newtonian dynamics being falsified, the reason that they introduced relativity theory, because they had nothing left to go with. But if they agree that light was a constant and that you couldn't use it to measure relative motion, then you would be good to go. Now, that was falsified later with the Sagnac effect, where he shows that you can measure rotational motion with an interferometer on a velocity that's not even moving at relativistic speeds with the first order effect, of the velocity proportional to the velocity. So in 1915, they said, okay, here's what we're going to do. Rotation is considered an acceleration. It doesn't fall under special relativity. We're going to incorporate it under general relativity, and we'll use the equivalence principle for acceleration and gravitation. And that was kind of the jumping off point where they were reconciling that. So then they changed the orbit from going around the sun to now we're on a curved linear path, right? Which is a nonsensical term. How could it be curved and linear at the same time? But that's where you get into, well, that's a gravitational well. Well, let's back up for a second. So what's this gravitational well based upon? So here we're introducing big G now as a coefficient to distribute the gravitational energy that they say you would have, or I'm sorry, where you're conserving mass as a gravitational field, and then you're using big G as a coefficient to distribute that over the space-time coordinate system. So what you're doing is they're just reifying the same two theories together without even though the dynamics of the first one was experimentally shown to be false. So the predictions, like it's kind of like a sandbox with a blank slate, essentially, right? Because in relativity theory, what do? You take two bodies, you break them down into their own individual infinitesimal coordinate system, right? So it has its own section, its own slice of space-time, right? And then you're going to analyze the effects, right? And you're going to analyze the effects between them and draw angles between the center of them, and you're going to get your bending and warping relationship, right? It's all a fantastic system, and it has practical application. Like, for example, in engineering, you can use the same kind of tensor calculus to analyze like the stress of an I-beam and whatnot, right? By defining an arbitrary coordinate system to get the dimensions of the I-beam, and then you would introduce your stress, at specific points, and you would get the same kind of situation. So it has practical application, right?
And it's also been experimentally proven on scales that are relatively close to us, such as the experiment with the star bending around the sun.
Oh yeah, we'll get to that.
So we've observed the bending of reality that light goes around.
Ooh, so we will absolutely get to that here in a second. Let's see, where was I about to close up on something that was super important? Does anyone remember?
You were saying about the midnight redshift and something else.
Yeah, I can't remember. But yeah, so let's go with the local predictions of general relativity, right? Because like you were saying, to get relativity theory off the ground, to really solidify it, it had to to supersede Newtonian dynamics and become the causal mechanism of gravity itself, right? It had to be observed experimentally. So they came up with the derivation for how much starlight would be displaced under relativistic effects. So what they did was they said, okay, we have the sun, and we're gonna predict how much starlight would be displaced based off of the gravitational field, right? And this prediction is geometrically different than the gravitational prediction that would be used for Newtonian dynamics, right? So in their conceptualization of it, this is like supposed to be extremely meaningful because of this distinction, right? So this is how one supersedes the other and becomes like a more accurate approximation at this quote unquote, relativistic scale where you get to the mass of the sun, right? It's like, damn, like, what do you do with that? Do you use a regular scale? And like, no, you need that Einstein scale, right? So anyway, as the fable goes, Eddington sets out for his observations, and he found relativity right where he was looking for it. Now, the history of the observations is a little dubious, but I found some subsequent observations that kind of support it, and there seems to be like a back and forth on it. So I'm not even going to fully discredit Eddington on that. Let's give it the benefit of the doubt and say that there is some starlight displacement. Now, what people have observed primarily, and we'll get to the special case here in a second, which was brought to me by McToon. Shout out to McToon. But what primarily people observe is near the limb of the sun, where there's already assumed to be a medium of plasma and magnetic field, electric field, different gas, what have you. There's already assumed to be a medium there, that there's a little displacement. So that you could say maybe the refractive index XYZ could be doing this, right? And in addition to that, there was one other experiment that was verified from what would it be? What's the word? Solar radii. So 7 solar radii out from the sun, and that prediction, when you're 7 solar radii out, the prediction of the displacement would be 0.02 arc seconds, something like that. It's something
I
insane.
believe you're close. Yeah, some is ridiculously tiny.
Yeah, you would never be able to optically determine that terrestrially, right? So what this guy did is he has a very in-depth statistical analysis on the lens that he used, on the refractive, on the atmospheric conditions, et cetera, and some reference tables from the Gaia satellite, what do you call it, probe thing, where they were taking parallax measurements to get quote unquote the actual positions of the stars or where they should, expect them to be. So after this comparative analysis, 7 solar radii deep, 0.002 arc seconds into an observation, he's like, yeah, I confirmed it. But let's go. Okay, so we've got some maybe it happens, maybe it doesn't. What is it? Well, in 2013-ish, Edward Dowdy Jr. came along, a plasma cosmologist, and using the same equation that Einstein used, essentially the same formalism, right? Just different variables. If you assume the sun is a Gaussian surface and all that, instead of being a mass with a mass attracting mass, it's going to be a Gaussian surface, so it's going to have an electric field, and the flux of that field and all that's going to be an even distribution, so that it just has a nice equidistant gradient emanating from it that drops off at the same rate that gravity would. So instead of having big G and big M, you're going to have big M as the charge potential, and then G is going to be that charge potential radiating outwards, right? So same exact predictions. And it's like, okay, so now what do we do? Is it due to an electric field gradient situation, or is it due to the bending of warping of space-time? How do we get a more in-depth analysis, right? There was the second proposal, which was along with, because there wasn't just gravitational redshift that was put forward. This was like a multi-year battle, starting with gravitational lensing, right? And then there was, what was the other one? It was the perihelion precession. We didn't cover that one, but that one's not really that good. That's just that could go either way as well. But the big one for everyone was gravitational redshift, because that would actually provide like a mechanistic shift in light that they would measure, and they could attribute that specific shift amount to, okay, in order for us to get this frequency, and to kind of put it into easy to think about perspective, right, is they're saying that if you take starlight, split it with a prism into a rainbow, there'll be like a certain shade of red that you'll get, and that frequency they produced by a certain frequency, right? So they're saying that starlight interacting with a gravitational field, when you look at it through that spectral analysis, will produce a certain type of redshift. Right? Yes. And it's like it's a very minuscule amount or whatever, right? But they say that they extrapolate this out of the equations, right? So
yes, that may also determine which direction you would be going.
Yep. What did they do for the first redshift? Was that just from? Oh, that was. Oh, I'm sorry. Yeah, that was with the lensing. So okay, yeah. I totally forgot about that. My apologies. So in tandem with the gravitational lensing observation, there was predictions for the gravitational redshift. Now, there were two gentlemen, John St. John. No, that's not it. John Evershade, and St. John. Sorry. Those two gentlemen were the world leading heliospectroscopists at the time, and those guys were tasked with analyzing different starlight and different light from Venus transits of the sun at different times of the year, to see if they could match gravitational predictions from relativity theory, and they couldn't match a single observation. And before Eddington went on his gravitational lensing expedition, he wrote to Swiss mathematician Hermann Well and was like, yo, bro, we got the lads out here trying to figure out this gravitational lensing prediction, because people are asking for an actual physical mechanism here instead of just, abstractions in the sky. And they're not getting any measurements that are giving any agreement. And I know you're working on a new theory of gravity. Can you help us out here? So Eddington was, fully aware of these measurements and stuff. And when it came down to it, they announced the successful confirmation of relativity theory through the lensing, and they completely ignore the fact that they couldn't get any gravitational they couldn't get any gravitational redshift to correspond to it. In other words, the causal mechanism, couldn't be established of, was the photon so-called, was the redshift due to the interaction with the traveling around the bending of the gravitational field, or traveling around bent space-time, which is due to the curvature or due to the intensity of the gravitational field, like relative to the strength of the gravitational field that it's encountering, right? So they couldn't establish a causal mechanism, but they went ahead and pushed it forward anyway. And then later in 1965, there was the first, what I would consider the first laboratory experiment of gravitational redshift, where they did pound Snyder and pound Rebka in 1960 and 1965. Are you familiar with those? Actually, I just went over a lot. Do you want to talk or say anything?
Yeah, I'm bored.
Yeah, no worries. That was a ton of info. So if you guys were, wait, was that Ruhif?
Yes.
Oh, I thought that was dude. I was gonna say, damn, my bad. Didn't mean to sleep you.
Can you still hear me?
Yeah.
Yeah. But we have observed redshift now due to gravitational, the bending of space time.
Yep. We're about to get to that. I just wanted to make sure that you didn't have any questions.
Okay. Yeah, I'm still tracking. Now the other people might be totally lost because this is really into the weeds.
Yeah. This is as far as the weeds that you can get, dude.
Yeah, so, this is we out there in the bush now.
So Pound Rebka in their 1960 paper, they said the title of their paper is "The Apparent Weight of a Photon," and when you read the paper, what they mean by that is that the classical theory of how a photon would interact with the gravitational field, experiencing frequency shift, as if it falls faster due to gravity, and then the relativistic, the Einstein prediction would be that the speed of light is the same, but the frequency shift happens in proportion to that ratio of gravity. But they actually make the same prediction, and what they're doing with the Moss-Bauer detector in that experiment, which is a Moss-Bauer detector, for those who don't know, what they're doing is they're essentially just ionizing energy and converting it into an electric signal, and they expect a certain pulsation rate based on X amount of energy. So this detector that they have will only accept a certain amount of frequency, in other words, a certain amount of energy. So when they emit a photon at the top of a tower, it has to be at a certain energy level for this detector to convert it. Right. So they got their detection, and they were like, okay, well, here's the thing, boys. Apparent weight of the photon. It could be either or. Could be relativity. Could be that the speed of light actually changed. Right. We don't know because it's a Moss-Bauer detector. So they went ahead and did the same experiment again in 1965, but instead they used a gamma ray, and this was to eliminate make like the Stark and Zeeman effects, so frequency shifts that would be due to magnetic and electric fields. Yep. And they got the same frequency shift again, and they were like, all right, boys, here's the thing. We're not making any specific comments on relativity theory or anything like that, but we got could be either way. We should do it again with atomic clocks so we could time it and get a definitive answer. Because if relativity is true, then it'll get that signal at a specific time and not before it, right? So
yeah,
they ended up never doing that. So the best case that I could give you would be, are you familiar with you're familiar with the Sagnac effect. So there's vertical interferometry where people have done a Michelson-Morley style setup, and they've done it vertical, and they've gotten proportional fringes. I think it was, what did that one guy get? Was the one guy said he got just over 2 fringes. But again, I haven't seen these guys' data or anything. It's just like YouTube videos. It's hard to analyze what they're doing. But there was one guy who published a paper recently, but it's $28. I haven't bought it yet. But he's saying that he, did more accurate reproduction of it, etc. Got two fringes on it. Yo,
you know about Sci-Hub?
Yeah, it's not published on there.
Okay, all right.
Yeah. Otherwise, I would already swooped it. It's on some third party, like what do you call it? Like a private venue type thing where he did his presentation
Smart.
on it. Yeah, but anyway, he got his measurements on the vertical, right? So what that would show, obviously, is that the speed of light going up and down, there's a preferred direction, and it's not isotropic; it's anisotropic. And then further, what they'll do in modern times is they'll go, okay, we have an atomic clock, and this atomic clock is processing in accordance with gravitation theory, and we're using that as a proof of the redshift, right? Because the frequency shift inside the clock is shifting in accordance with the prediction of relativity theory. But with the atomic clock, you're running into the same problem with the Mossbauer detector, because how the atomic clock works is it's again an ionizing what is it, cesium and radio frequencies that are oscillating at the same frequency as the cesium to get an electric signal that they convert to get their oscillation rate or the frequency for 9.192 gigahertz. So it's not you would have to do maybe you would have to do like the Pound-Repka experiment with atomic clocks, the time, the propagation rate, or you would have to do like, vertical interferometry, which the ones that have been done support, a variance in the speed of light.
Oh, I don't disagree. There's variance. I actually think I actually think it actually way more complicated than that. I think the light's choosing its average speed. We can see at certain points around certain massive objects, and this is something very few people point out, but as the light tries to come up the gravity, what we call as the ball's spinning or orbiting or whatever it's doing, and there's like a cavity there that the object's spinning in between the fabric of reality. The speed the light goes up to climb over that is faster for some odd reason than it does it when it's decelerating off the curve. And that's something I think is quite interesting and quite telling. So if you're, say you were looking at a black hole and you have the disk around it, the flame, of course, it's not actually flat like a planet's ring. It'd be three-dimensional because it's bending space-time in theory. As it's bending that, is the light reflecting off of itself and gaining momentum as it climbs up the well, or is it just accelerating itself to climb up, not before it falls into the ring, but the actual, say, the next wave over. The next wave over, you would think that the light should decelerate downwards with the wave as it's going. As far as I've found, no one has been able to come up with an explanation for this, and I don't know why. Which is the accelerating up in theory, the ripple as it's going out. I don't know how to explain that. I don't know what instruments you could use to come up with a theory for that. But as far as I can tell, with the latest experiments with light, like I'm sure you're aware of the split light experiment, right? What's it called?
Double split.
Yeah, the double split experiment. But I'm also sure you're aware of the time split test. They also done like the opposite way.
The old quantum eraser?
Well, here's the thing. So they fired two beams, and they were, I don't remember if they were staggered. Oh yeah, they fired one and then fired the other and then fired them at the same time. And what they found was that the one and they don't talk about this, that the one that they fired later somehow came back and informed the first beam about which direction was the path of least resistance.
Alan has a really new, cool revelation about the delayed choice and the quantum eraser. But before he goes into that, I just have one question. I'll go back on mute. You mentioned something interesting about Euclidean behavior of how light dips down a gravity well and comes back up and having to accelerate. I put something in the nest, the latest thing. Although that does seem rational, you do understand under the model, one of the postulates means that it can't do that. It absolutely.
Yeah, that's why I said it's definitely flawed, because if you're an extremely, in the details kind of guy, you'd see things like this that shouldn't be there. I mean,
Well, I'm glad
Einstein
you're honest.
himself,
Einstein
himself didn't believe there would be black holes in this theory.
Well, I'm really glad you're honest about that, and that's appreciative. That's rare around these conversations. But you do understand, if you deny that, you pretty much break the entire model around relativity. You can't operate with a variance in C. But I'll let Alan continue.
Yeah, so the variance in C is actually, can't happen in relativity theory, because relativity theory is supported by the principle of relativity of simultaneity, which as a consequence of the constancy of C, that's where you're going to get this ability where time and space have to be merged to compensate for that, based off of either your relative velocity or your gravitational potential. So what we were so anyway, if there was variance shown in C, that would mean that the speed of light is changing and not time and space, right? That would be indicative of an absolute time and an absolute space, which we'll come back to shortly. But there was what was the other right, the quantum eraser and which way and delayed time and all that stuff, right? So for the double slit experiment, no one's ever seen the pattern that corresponds to light being a particle. They only see the diffraction pattern of light being a wave. There's a really nice video of a lady on YouTube called Looking Glass Universe. During the COVID lockdown, she did the experiments in her apartment, and found and used fog to kind of visually show the different intersection points of the waves as it's recombining from the diffraction pattern to create the pattern that you see on the wall. Definitely indicating that it's not a particle at any time and it's a wave. She was surprised by this because she has a PhD in quantum mechanics, and she actually, the way that they teach it is that the wave theory is the abstraction, and the physicality, the meaningfulness is the particle, right? She was like kind of blown away by that. And then there's another example here by Sabine Hoffenstetter, where she spills the beans on the quantum eraser, which way, delayed choice, delayed time.
I'm aware of her. I like her work. Yeah.
Yeah. So what she says about it is,
funny German lady.
What she says about it is that the way that they have the detector set up is that it's just splitting the diffraction pattern between the two detectors. Nothing's going back in time. When you superimpose the patterns together, it makes the same one that it always made, and it's just a cruel trick. Like the illusion that the observer changed it and all that, and like retrocausality, and the light went backwards in time.
I would disagree with her, because the light beams are leaving two different times, and they have the negative correspondence of the adjacent wave retracted from them. So, like you said, when you combine them, you could see the original waves. But what they found was the first laser acted as if the original form was there, and the second laser didn't. And the second laser had the form that it made out when the pattern was made was part of the pattern subtracted. And so the idea was that the pattern gathered its choice from the second pattern, which was fired last, not first.
Oh,
And
I got you. I got you.
and so they
Yeah.
think, so in now this is trippy because it implies that light itself may be, to me, it may be semi self-aware. Um, the light itself, it would imply that the light itself is going through time, for like looking at the future and coming back and telling itself what's the best path to take. And so it's somehow semi informing itself of future events. And it's a very frightening concept because it implies, what does that even mean for all of science? Because it would imply that, well, in theory, you couldn't know anything that wasn't already decided for you to know. In essence, every experiment itself, in theory, could be thrown into the air if it's true that it's informing itself, because then you would only be getting the results that it informs you to get. So I think they haven't. She brought up a good point, but I don't think she missed the significance of it and why they haven't pushed any more on it, because it's a very, it's like taking a chisel to the very bottom foundation of all of science. Because if light is somehow informing itself from the say, like, the present is already being informed by light that was both coming from the past and the future, I mean, what could we do to even test anything anymore?
Yeah.
I mean, in essence,
Yo. Yeah. So, uh, the quantum eraser experiment, I think you're thinking of a different one because that's done with the in phase, right? They're not sending it in a different thing. So when you emit light at two different time intervals, it's not going to ever be in phase, and any diffraction pattern you measure of it is still going to be a wave. Like, you can't really get around. It's always going to be a wave. And you're like, oh, how can we
yeah.
measure? Well, hold on one second. You're like, how can we measure a cohesive timeline or like know anything about it? Like, well, those V over C predictions and interferometry is how you could know, right? Those are all based off of a specific timeline of the time in the lab frame, right? But it's measured against absolute time, or I'm sorry, absolute time and absolute space, right? So that's how they get the measurement. So if that's not the case, then there couldn't be a measurement, right? If C was a constant speed, right? The only way that the measurement could be made is if it's with respect to absolute time and absolute space. So they're not,
Absolutely.
yeah. So they're not just like to main. So to okay, that's great. So to acknowledge those and to understand that, but then to say that they're like intertwined is incoherent because they're absolute, right? You could
Well, the
measure
thing
against
is,
it.
we wouldn't know what light came from the future or the past, in
Well,
theory.
yeah, but you gotta kind of understand though, like what you're saying though isn't it's not applicable to the situation because the pattern that they're getting in that reading doesn't change. It's never not the wave, and you can and the like it's always the wave, and like
Oh yeah, it's definitely the wave. The wave function is definitely happening. The wave function is definitely happening. The question is,
so what is it you think is happening in this time
do you
interval thing?
my theory? Well, first off, I think the universe is clearly created by God. I think there's
Wait,
definitely
hang on. What's the name of the delayed time interval light
uh,
experiment? Real quick.
it's literally something like that. The time split experiment or something like that. I can't think of the name of the experiment off my head, but it's basically the same principle, but with time rather than with light. But now I'm trying to think of the name. Maybe the double time split experiment or something like that. Um, don't quote me exactly what the name of it is because I don't remember. It's been a year or so since this came out. Or
You sure it's not the delayed choice?
Don't hold me to it because I don't remember the name. It's been a year and a half since I read it. But I think what's actually happening is you have light that serves its purpose somehow, and then takes off and goes to the end of time, and somehow or close to it, and then comes back. So there was a idea, a concept. So that light isn't actually the fastest thing in the universe. That the actual true fastest thing in the universe is the explosion of a connection between two certain neurons. I can't remember what they're called, but there's a experiment they did where they showed that the light itself is traveling so fast in between them that it disappears and then reappears on the other neuron. And so, in theory, if light has this upper bounds limit to where it can literally just like kick on the afterburners and just split time itself, the wave function itself would the wave function itself would be a predetermined event. Would
Yeah,
be the
but
implications.
well, you're kind of just
Can
asserting.
I chime in about time?
Yeah, go ahead.
Oh, before you do that, I was under the misunderstanding that you adhere to the mainstream science, but clearly you don't. But just one thing you have to say about time, even mainstream science doesn't say that you can go back in time. Theoretically, you couldn't even have this as a hypothetical because you disrupt cause and effect. You
Yeah,
uproot,
you would,
uproot
but
cause and effect.
a
And that
particle
causes a lot
writing.
of paradoxes, including like the grandfather paradox and a number of different paradoxes. And you can't have paradoxes in reality because they're contradictions. But go ahead, Keith.
Yeah, I was essentially gonna say kind of the same thing. Like, you're talking a lot about time and disrupting time, and you can go back in time, and it's informing itself because it's going faster in time and coming back. Like, we got to understand that time is nothing but a human measurement of change. You can't go back in change. Once the change has happened, it's finished, and you can't go in future change because the change hasn't happened yet.
Well, the implications is that uh, time is going all directions all at once at the same time.
No, you're failing to understand the concept. Time is a measurement.
Yes, yes.
It's a
But
system, right?
as light gets as you get closer and closer, not a human, but anything that gets closer and closer to the speed of light, time itself begins to slow.
No, it doesn't. That's a falsity. That's one of the problems with general relativity. So you got to get yourself out of that mind frame and stop thinking that time is something that can slow. The only way time slows is if the mechanism that you're using as the measurement slows. But that's something that's done mathematically. That's not something that's done in reality, unless you're using like an atomic clock or something, and you're changing the rates. You're using a different material that oscillates at a different rate. The oscillation there, but you're still using like a clock in that sense, you know. So it's a measurement with an oscillation. It's not what's actually happening. It's mathematics being applied to what's actually happening. So there's no slowing of time. There's change that's happening. This is what I'm saying. This is where physics gets into the math and stops recognizing what's actually there.
Go ahead.
Oh, I was saying we're talking about something moving at near the speed of light. Space itself would be going by so fast that objects itself would stretch with the light.
That doesn't even make sense, man.
Plus, you got to accept that without prior derivation. I put something in the NAS. I won't play it again. I played it a couple of times for the group, but it basically talks about that. What has a cosmic speed limit that moves at that speed limit to negate an ability to calculate time doesn't equate there being a speed where time itself stops. That's reifying a concept that we use to measure change, like D3 says, into something that's a medium or a light line or a world line in a coordinate system. What happens with special relativity, it reifies a coordinate system. It takes a light line, a world line, and a space line, and it puts it in a flat plane, which is usually used for a surface, and it says that is your 3D reality. Like graph paper, we'll put something on this graph paper, and as you see that world line and space line bend, that's how space and time is bending. These are all fantastical concepts that people have to accept to explain away what we know. Like you accept, which I'm surprised that light has a variance, and
Yes.
you can't accept light having a variance while accepting the bending and warping in space time. Those are
Yeah, I can. If the light is traveling into the future and coming back, or in the past and coming back, it would have, it could exist in the 3D space time.
Yeah, I wouldn't even know how to start to approach that, but I don't know if Alan
All
has
right.
anything
Well,
to add.
let's look at these. Say we have the center of the. Let's say we quantify and shrink the universe into a tiny little dot, and that's all the possible light that would exist at that moment, and then it explodes. It explodes in all directions equally fast, right?
Yeah,
But
it's
it
like
would only give that
the
appearance.
expansion. You're talking about the great
Yeah,
expansion.
but it would only give that appearance if either two things, either well, three things. Either it had a consistent speed, something was acting on the opposite side of the universe. Say, like God was clutching it in his hands or something, and it was resisting that clutch. Or speed, the speed of light varies according to the distance and the relative curvature of the space that it's going through. And if it needs to accelerate, it can. And if it doesn't need to, it won't. That's why I said we have this odd event where it actually speeds up the trough of one of the gravitational waves. We can observe that with the black hole and the oscillating disk around it, where the hottest part of that fire is. We can see it, and it shouldn't be at the bottom of the 3-dimensional image. So the disk would be like halfway across the black hole and then halfway up it. We shouldn't see the hottest. Well, we don't see it; we measure it, but we should be able to measure the hottest part of that curve at the intersection, like the as it's going up. It should be at the top when it's as now it's got full momentum, full kinetic energy. As it rolls off, it should actually accelerate faster down than it does going up. But for some reason we observe it accelerating up against the resistance. And the only way the only way I can figure that out is if it's aware of that resistance at some level. Because if it falls on the other side of that trough, in theory, then it would be in the actual what do you call it, the event horizon, and there'd be it would almost be forever lost in theory. But we can measure where that hottest part of that fire is, and it's in a particular spot. And like I said, as far as I know, there's no theory that can answer this, because it actually acts contrary to what we observe in any form of reality. That's like within a sane reality, we don't observe anything being other than something that's conscious, being aware of an obstacle and like pushing itself forward harder. Now they'll say that that's because that's the near the. I have heard them try to explain that it's because it's near the accretion disk, and the heat of the friction of that is going on, and there's some light that's escaping, and right at the edge, like maybe the tiniest little wiggle is in there, so it finally can spring forth. But I think once they set the limit, that's where it collapses. That's where you can no longer escape it. When you start making ideas like, well, maybe there's a tiny little edge of the wiggle in the event horizon, and it's getting all this energy, but then it's finally breaking loose, and that's what's causing. I don't think that's a sufficient answer, and I
Yeah,
also don't think
you
any
have
other theory has it.
you have a lot going on with space time on the mind. Maybe a diagram would help, but you have sentient light that it's aware of itself, going in and out of time backwards while keeping relativity, but not keeping relativity with the variance of light. You got to understand it's a very confusing to try to keep up with. Maybe somebody else caught that, but you have a lot going on. Maybe a visual, but I'll land it with this. There's contradictions in your model. You can't have a variance in C and keep the standard model. It just can't. It breaks. They need those two postulates.